In our previous video, we have studied the ways in which we can calculate the enthalpy change of a reaction by applying the Hess law and using the enthalpies of formation and using the standard states, that roof that we were talking about. This approach, which by the way may be useful to know the enthalpy change, and you may be wondering, why would I be even interested in knowing the change in enthalpy? Well, if a reaction is going to give off a lot of heat, and to the point that it's explosive, it may even save your life if you have calculated that enthalpy change ahead of time. So we have even a formula, if you will, for calculating the change in enthalpy by applying heats of formation, and being the coefficient, you add up all the heats of formation of your products and subtract all the heats of formation of your reactants. Sorry, there's an F missing here. Where N is the coefficient on the balance reaction of that specific compound. So let's practice some more. In this case, we want to know the change in enthalpy for the burning of ethanol liquid. So the change in enthalpy for this, sorry, it's not the formation anymore, is the change in enthalpy of this reaction will be the addition of enthalpy of formation of these two. So let's start. 4 times the change in enthalpy of formation of CO2 plus 6 times the enthalpy of formation of water, and careful here, it's water liquid. So in here we have 2, we will have to use this one, negative 2 times the enthalpy of formation of ethanol liquid, C2H5O liquid, and sure, we would do 6 times the enthalpy of formation of oxygen, but oxygen is already an element in its standard state, therefore in our roof, and by definition this is 0. So if we apply this, 4 times the enthalpy of formation of CO2, it has to be gas, so 393.5. Now plus 6 the enthalpy of formation of water, it has to be water liquid, so that would be negative 285.8. Now negative 2 enthalpy of formation of methanol. There's a lot of negatives here, just make sure you keep track of them, okay? And this will give one of the answers. Hopefully, let me see, this is going to be around 12, 13. It's going to be fairly negative, so it's going to be one of these two. I would need a calculator to do that, but everyone can do that, hopefully. Okay. Now let's apply this knowledge to a somewhat different case. In this case, we are being asked to calculate the enthalpy change for this reaction, but notice that now the standard state is a different one. We send the molecules to a different roof, if you will. We just need to come up with the right standard for everyone. So it's giving us the energy that it takes to break or form each of these bonds. So the enthalpy change will be, for this case, the enthalpy to form bonds minus the change in enthalpy to break the bonds. So in this case, we are going to send the reactants to all atoms, and then we will form the atom. So we're going to break all possible bonds here, so that we only have oxygen, hydrogen, and carbon, and then we will recombine this oxygen, hydrogen, and carbon into the molecule of ethanol. This is our new roof. This is not the standard state that chemists have agreed upon, but it's a new roof, and we have all the necessary information to do that. So again, the change in energy will be this minus this. So let's see if we can do that. How many carbon-hydrogen bonds are we forming? We're forming 1, 2, 3, 4, 5. So 5 times and because we're forming, it'll take the negative. Okay, it gives off energy to form bonds. Now, how many carbon-carbon do we have form? We have 1, so this will be 1 times the carbon-carbon, which is 350. And now we have 1 carbon-oxygen, so 1 times carbon-oxygen, so this will be, I'm sorry, did I already count that? No, carbon-carbon, oh yeah, carbon-carbon and carbon-oxygen are the same, okay. And finally, 1 oxygen. That will be the formation of the bonds, and notice that all of them are negative. 1 times 1 bond of this one, so 460. Okay, and now I'm going to subtract the breaking of the bond. I have to break 1 carbon double bond, so that'll be 1 times, and this time is not negative. Alright, so of course then it has to be positive. Alright. Now how many carbon hydrogens that I'm gonna break? It's 4 times carbon hydrogens, that is 410. Okay, I'm done with this molecule. Now I need to break 2 oxygen hydrogens, and that's 2 times 460. And this will give a number, whatever that is, hopefully is negative, because the I would say the ethanol is more stable, so I'm gonna bet that it's probably negative. But again, this is just a way to show that you can come up with a different reference point other than the standard state that we defined, which is the molecules, sorry, the atoms in their most stable form. Notice that if the other roof, the other standard state would have been oxygen as oxygen gas, O2, hydrogen as hydrogen, and carbon solid. This is the other standard state, which is a different route. However, because enthalpy, we say that is the state function, it doesn't matter what route you use, as long as you can close the cycle. This is the whole Hess law principle. We can successfully calculate the change in enthalpy for the reaction that we are interested in.